Okay. Hi everyone. This video is an intro video to walk us through the blood buffer lab that we're going to do this week. All of the questions will be like for example, the questions down here in the data, and especially the post lab. The post lab begins right here. I don't know why the header is on page 5, but it really begins on page 6. So all these questions in the post lab I will put onto a Blackboard assignment, so you're not actually going to answer the questions on a sheet of paper. You will answer them in Blackboard. There may be some questions, like actually 1 and 2 here. You will work those on a sheet of paper and show your work. But anything that's like a short answer where you just explain questions 3 and 4, those will be on Blackboard. But however, I'm going to walk us through this lab, and that way you guys can hopefully do it with a little more ease. I think it's one of the more challenging labs we do in the semester. But I will say, I'm going to pause right here. If you have not finished watching the acid-base videos, do not attempt this lab yet. Okay, so I'm gonna first right up here. First, go finish watching the chapter 10 acid base lecture videos. Okay, because in those videos towards the end, the last videos I post about buffers, they detail our blood buffer system and how things shift and respond and what a buffer is. So if you have not watched those videos on what a buffer is, just reading this first page is not going to be enough. So go watch those videos first. They don't take a long time. Take notes on them, get a better understanding of buffers, then come back and attempt the lab, okay? I'm not going to walk through this information up here. You can read these things. There may be some pre-lab questions on this. We'll see. However, here is where I want to pick up, okay? Blood pH. We know that the blood buffer system does a good job at keeping our blood between these numbers, 7.35, 7.45. And here's how it does it, okay? We have CO2 and water in our blood, okay? And when CO2 combines with water, it forms carbonic acid. Here is carbonic acid right there. And this reaction is catalyzed by an enzyme. But carbonic acid, then it's an acid, so it dissociates into bicarb. It's the conjugate base. And here is the acidic hydrogen. Okay? And this is what affects pH. Okay? Additionally, if you have not watched the Chapter 10 acid-base lecture videos, you're missing out on a key relationship that I wrote in, I forget which video, but you need to know this relationship. The reason why H plus affects pH, as you increase your concentration of H plus, as you have more of it in solution or in your blood, pH drops, okay? pH goes down, okay? And as we have less H plus, if it reacts with something, if it gets neutralized by something, pH raises, okay? This is very important to remember. Memorize, yes, but to know and be able to apply to this lab. So this is the buffer system we have going on, and here's how it affects pH. And then all this is saying down here is that because the enzyme's so efficient, we really don't linger on this middle step very long. We don't have carbonic acid sitting around. It's just either disassociating or it's shifting back towards CO2 and water. So we really just eliminate that from the reaction to show you our reactants and our products, okay? Now, I'm going to erase these lines I just drew because I want to show you what's going to happen in this lab. What we're going to do is we are going to add water, okay, which is a reactant. We're going to add water to a flask. And water, we know, has a neutral pH. What is the pH of water? pH 7, okay? We are also going to be breathing into the flask. When you breathe, our breath adds CO2. And according to Le Chatelier's principle, what that does is when we breathe into our flask, we are actually increasing the concentration of CO2, right? And if we increase the concentration of CO2, how will equilibrium shift? Equilibrium will shift towards the products. That's what Le Chatelier's principle says. So when we breathe in our flask, we're going to create more bicarb and more H+, okay? Then that's going to drop pH, okay? When we increase the concentration of H+, pH will drop. We've already said that, all right? Then what we're going to do is we're going to add NaOH. Okay, NaOH we know is a strong base. And what's going to happen when NaOH gets added to the flask where we now have bicarb and H+, NaOH is going to neutralize this H+, okay? So the OH minus and the H+ are going to react together to make water to neutralize. And what's going to happen when we remove H+ from solution, what's that going to do to pH, okay? As this, I'm going to extend our arrows so that I can add something in here real quick. As these react together and make water, what's happening to the concentration of H+ in the flask? If we're neutralizing it, then as we add more NaOH, we're decreasing the concentration of H+, and subsequently pH is increasing. All right. Then we might add enough NaOH that we have some excess OH minus, okay? If we add enough or too much NaOH, we will have leftover OH minus. All right, so we're going to be adding drops of a solution of sodium hydroxide. It'll be reacting with our H+, neutralizing it to make water, and at some point we might use up all the H+ ions in solution and we'll have some OH minus left over, okay? So as you watch the videos that are posted on each part of this lab, there's 3 parts. Remember what I'm talking about here. We essentially have 2 reactions. We have this blood buffer system with the CO2 in the water, and then we have NaOH reacting with the H+, neutralizing it to make water, okay? And the indicator, what indicator are we adding? I think it tells us somewhere down here that we are going to be adding an indicator which is phenolphthalein, okay? So the indicator is going to be clear when we have a pH that is acidic. I'll just write clear at acidic pHs, and then it becomes pink at basic pHs, okay? So acidic pHs means we have a lot of H+. Basic pHs maybe means we have a lot of OH minus, okay? And very little or no H+. Okay, none of it, or very little of it. All right, so keep that in mind because you're going to see these color changes as we breathe into the flask and as we add NaOH. We'll get color changes from clear to pink and back to clear. But that's just a little bit of the walkthrough on what we'll be doing in the lab and the actual chemistry that's going on. Okay, let's go down to the post-lab questions then. By the way, in the videos, we're only doing 1 trial, so we are not doing trial 2 for any of these, so we're not doing a round 2. So if you have to fill out any data sheets or do any work, which you will, just know it's for 1 trial, okay? Yep, so we'll have a part A, we'll have a part B, and we'll have a part C. So we'll have 3 different videos you'll watch that correspond to these 3 sections. Then I really want to get to the post-lab questions. So part number 1, post-lab question 1. This one asks you, hold on just a second. This one is asking you, it says deionized water has a pH of 7. What is the H+ concentration of deionized water? What is the OH- concentration? If you have not watched videos 10, 11, or 12, the acid base, that's chapter 10 videos, and that is numbers 10, 11, 12, those videos. If you've not watched those yet, you're going to be confused on what this question is asking and how to answer it. So go watch those videos first. As far as showing work, there is an equation that gives us the answer to this, okay? And you can either take the pH and solve for the concentration of H+, and then use kW and solve for OH-, or you can talk me through it from knowing kW at neutral pH of 7 for pure water. Okay, number 2, remember we're not doing trial 2, so we won't fill in any of those blanks. But number 2 says using the number of drops in table, what is that, 6A up here. So I will have these filled in for you on Blackboard, or you'll be able to get the numbers from the videos as well. What you're going to do is, it says calculate the moles of NaOH necessary to turn the solutions pink. Show all your work and fill in the values. Well, you do not have to do the calculation 4 times. So the first thing I'm going to say is only show calculation 1 time. Okay? So we're trying to calculate moles of NaOH. And what we're going to have is a number of drops. That's what is going to be up here in this table, drops of NaOH, and that's what you'll determine from the videos as well. So we're going to start out with a certain number of drops. Let's say it took us 5 drops to turn the solution pink, drops, and that is of a solution of sodium hydroxide. How do we convert this to moles? Well, if you read the last of the question, it gives us a conversion factor from drops to milliliters. So the first thing you're going to do is you are going to convert from drops to milliliters. Then we know if we're going to get moles, and we have a volume right now, we have milliliters, we're going to be using a molarity. The molarity, next thing you need to know, if you read the procedure of this lab, which you should, even though you're not in the lab doing it yourself, read the procedure. The molarity of NaOH solution that we're using in the lab is 0.05 molar. Well, what does that mean? That means there is 0.05 moles of NaOH per 1 liter of solution. Okay? So we're going to use this relationship I just wrote out to convert to moles at the very end, but right now we have milliliters. We need to convert to liters, so you're going to go milliliters to liters. Last step is you're going to use the molarity, what we just wrote out down here, and you're going to go from liters to moles of NaOH. And please show how all the units cancel. Okay, now I wrote 5 here. You're not actually going to use 5 unless that's an actual number from the videos or the data table in Blackboard. You'll use the number of drops that are filled in on the table shown in Blackboard. Okay. Number 3 and 4, these are short answer. Okay, here and here. So there's no calculations, but what I really want you to pay attention to is the last part of the question. Let's read it though. It says, is there a rough pattern to the number of NaOH drops required to turn the solution pink in the successive rounds? So when you go through and watch each of the 3 videos posted in Blackboard after this initial one, you'll determine that. You'll know if there's a pattern or not. Okay, so that's just a yes or no question. Yes, there's a pattern. No, there's not. Make sure you answer that. But if there is, here's the important part. Describe. what the pattern is and try to explain the source of the pattern. Okay, if we find that it's decreasing the number of drops of NaOH necessary, why? If we find that the number of drops of NaOH needed each time after we breathe into the flask is increasing, why do you think it's increasing? Okay, make sure you explain that. Number 4, comparing the rest and exercise data. How did exercise affect the time of breath required to turn the solution clear? And then how did exercise affect the number of drops? So there's 2 questions here. How did it affect the time of breath? And how did it affect the number of drops of NaOH required to turn the solution pink? And then again, offer an explanation why. Why did it require more or less drops? Well, let's think about exercise really quick. When we're resting, our body is doing a lot, but it's not doing as much as when we exercise, okay? When we exercise, if we increase the amount of exercise that we're doing, we're putting our muscles to work, we're putting our circulatory system to work, our respiratory system, our breathing increases, it becomes heavier, right? When we're working our muscles via exercise, we're also increasing the concentration of CO2 in the body. All right? That's just a byproduct of exercise. Well, then think about how that affects your respiration. We're also increasing respiration. In the video, you'll notice the scientist is breathing heavier after he goes and exercises. And if we're increasing respiration, we have more CO2, more carbon dioxide in each breath we exhale. Okay, so as we increase in exercise, we increase concentration of CO2 in the body. We have to breathe that out. So our respiration increases, and then we are breathing out more CO2. We have a higher concentration of CO2 in each breath we exhale. So think about that as you answer this problem, okay? Walk me through that as you explain your observations, if that relates, and it should. The last part, by the way, we are not doing number 7, so you will not answer that. You're only going to answer question 5 and then 6A and B. Okay, so question 5 is talking about our indicator phenolphthalein. It says it's a weak acid and it has a pKa around 8. Again, if you have not watched the acid-base videos, do not try to answer these questions. Go watch the videos about good qualities of a buffer, pH and pKa and their relationship, so on and so forth, and then come back and try to answer these. But it says the pKa is around 8. The indicator changes color once the pH approximately equals pKa. All right? A simplified acid dissociation equation for the indicator is given below. Okay? HIN to IN minus and H plus. What does that mean? Well, this is the non-dissociated form. Okay, this is our weak acid. And this is the dissociated form of the acid. So this is our, I'm going to zoom in right here. This is our conjugate base. All right. From the videos, the lecture videos, I'm gonna come down here. I represented this type of equation a different way. We draw it in the buffer diagram. We say we have our weak acid HA. Here it's just saying HIN because it's saying IN is the indicator. So that's the weak acid. Instead of saying HA, they're saying HIN. So this is the weak acid. We know we're at an equilibrium in a buffer between the weak acid and the conjugate base. Up here in question 5, the weak conjugate base is IN minus instead of A minus. Again, don't be confused by that. And we say, remember I walked us through, if we add a base, okay, a base would threaten to increase pH. Well, we know a buffer wants to keep pH around its original, okay, around close to its pKa. So if a base is added and pH starts to rise, the weak acid is going to dissociate. It's going to give its H plus to OH minus, and they're going to make water, which does not affect pH. And then what's left over is more the A minus, okay? So equilibrium would essentially shift if pH starts to rise. The equation shifts right towards products, towards the the dissociated form of the weak acid. It shifts towards the conjugate base. And if so that's one point to remember. If pH starts to lower, and how would pH drop? Okay, let's say we have some H plus is added, okay? Or if pH is below pKa, up here we could say if pH starts to rise, or if pH is above pKa, then the equilibrium or the equation shifts left towards the weak acid. I cannot write today. Alright, so again, we walked through this. H plus, if this is added and it could drop pH, and again the buffer doesn't want pH to change, that conjugate base is going to scoop that up, react with it, neutralize it, and make more of the weak acid. Okay, so as you think through questions 5, 6a, and 6b, you need to think along these lines. Okay, this question in number 5 says which form is favored. Which form? So when it says which form, it's saying the HIN. Oh, not minus, just HIN. So the weak acid, or the conjugate base. Which form is favored? In clear deionized water, and in the pink solution. So there's two questions here. Make sure you answer both. Clear deionized water, you need to ask yourself, what is the pH of clear deionized water? pH equals 7, right? In the pink solution, what was the pH? You may not know exactly the pH, but you could guess that it was higher or lower than 7, okay? Then you need to ask yourself, based on what the pH was in the clear and the pink solution, how does that compare to the pKa? Well, we know in clear deionized water, pH of 7, this is less than the pKa. In the pink solution, I'll give you a hint, pH of the solution is greater than the pKa. That's why things change color. So now come back down here and think about what we talked through in this diagram. Okay. Question 6, it says the buffer used in part D has a pKa of 6. Did your buffer solution ever turn pink? If so, why did it take more NaOH to turn pink than the deionized water? If not, why not? Well, you need to think about when we have a buffer solution, how is that different than just water? What do we have in a buffer solution that we don't have in just pure water? Okay, in a buffer solution, we have weak acid present and conjugate base. We have both. So the fact that these two things are already present, how could that affect the addition of NaOH and how much we needed to turn the solution pink if it ever did turn pink? And then B, which form, the weak acid or the conjugate base of the indicator, is favored at the buffer pH? Well, what is the buffer pH? It tells us in the previous problem. When it says buffer pH, remember, buffers tend to keep their pH around their pKa. So when it says buffer pH, it's also 6. Keeps it around the buffer pKa, which is 6. So here pH is 6. Is this consistent with the color of the solution? Explain your answers. These last questions, 6A and B, are challenging. Is this consistent with the color of the solution? Well, what was the color of the solution? You'll get that from the video. If it was clear, okay, or if it was pink, think about what the pH of that solution is compared to the buffer pH and why it would have been clear, why it would have been pink, okay? All right, I hope that helps. If you have any questions on this as you go about it, feel free to email me. And